use this derivative to find all intervals where the function f of x is x squared minus 11x is increasing and the intervals where it's decreasing. So we're going to use these same two steps we just talked about. We're going to take the derivative set equal to 0, and then we're going to do something called making a sign chart to figure out if it's a positive derivative on the intervals that the function was increasing, or if it's a negative derivative, we're going to conclude it was decreasing on the interval. So our first step throughout this whole section, we're just going to take the derivative and set it equal to 0. So my derivative, f prime of x, derivative of x squared is 2x, derivative of negative 11x is negative 11. So there's my derivative. I'm going to set it equal to 0. And now this goes back to some algebra. So how are we going to solve 2x minus 11? If it doesn't have an x squared, if it's of the form mx plus b, right? This is a linear equation. There's no x squared in it. We do not have to factor. So I know a lot of you don't love factoring. Don't factor unless you have an x squared in the next term. Otherwise, if it's just an mx plus b like this, when you set your derivative equal to 0, you have to think about solving methods. And if it's not an x squared term, you want to just solve it like a linear equation, which means we're going to add the 11 over. We're just going to try to isolate that x, get it by itself. So we'll add 11, 2x equals 11, and then we'll divide by 2. So x equals 11 over 2, which you could leave as a fraction. Most of the time I will, because a lot of fractions don't terminate when we turn them to a decimal. But this one, 11 divided by 2 is just 5.5. So you could choose whatever makes you more comfortable. And it's because it's the first one, I'll change it to a decimal because most of you like decimals more than fractions. Anything but fractions, basically. So this x equals 5.5 is super special. It makes the derivative 0. What do we call something that makes the derivative 0? It's a critical number. So we want to call it what it is. It makes the derivative 0, so it's automatically a critical number. If it made the derivative undefined, it could still be a critical number as long as it's in the domain of f. It has to be able to go into the original. But since this one made the derivative 0, I don't even really need to worry about whether it can go in the original. And I know it could because 5.5 squared minus 11 times 5.5 is definitely going to give me a value. It's not going to make me divide by 0 or anything like that. When I plug it back into this original function, it's going to have a y value. It's not going to have an error. So there's our critical number. Our second step is to make that sign chart. We're trying to figure out, is the derivative positive or is it negative between our critical number before and after. So first thing you want to put on your sign chart is always going to be your critical number. And we're going to label it because it's something special. So I'm going to just do a little down arrow to there. This makes f prime 0. There's my critical number. It's not a random test value, which is also going to go on here. It's important. It's my critical number, so I just put an arrow down to it. And now I can choose any numbers before and after 5.5 to test. So before 5.5 is my favorite interval. Any interval where I can plug in 0. I love to do that because I feel like that's the easiest thing to plug in. So 0 is definitely before 5.5. You could choose negative 200. You could choose negative 1. You could choose just 4. Or 5 is still left of 5.5. I like to choose 0 when I can because it makes it easy to plug in. And we're always plugging in to the derivative. So let's make ourselves a note. Always plug in to the derivative on a sign chart. We want to know the sign of the derivative because the sign of the derivative tells us whether we were increasing or decreasing. It doesn't do us any good to plug into the original because that just gives us a y value. That tells us how high or how low we are on the graph. But you could have a y value of negative 10 but still be increasing at negative 10. So the y value doesn't tell you whether you're increasing or decreasing, but the sign of the derivative does. Right? We're trying to get to this point where we know if the derivative is positive or if it's negative. So that's what we're trying to determine. So if I plug in 0 to the derivative, I would have 2 times 0 minus 11. And I don't really care about the answer I get, I just care about the sign of it. So 2 times 0 is 0. 0 minus 11 is definitely going to be some negative number. And that would be true for any number to the left of 5.5. You could plug it in. Even 2 times 5 is 10 minus 11 is going to be negative. So even if you get really close to 5.5, you're going to see the derivative is negative, which means it was a function increasing, decreasing, or was it constant? It was decreasing. So I just draw myself a little decreasing line. It's falling left to right before 5.5. I can choose any number after 5.5. I'm going to put it in a circle. It's a random test value. I made it up. After 5.5, I would probably just plug in 10. I just like to plug in numbers that I think are easy to multiply out, but you can plug in whatever you want. You could just plug in 6 if you wanted to. So plugging into the derivative always, 2 times 10 is 20. 20 minus 11 is definitely going to be positive. So my original function must have been increasing. Here's a picture of what it would look like, and I don't expect you to get this picture perfectly the first few times at all. In a couple sections, actually, we'll be doing curve sketching, so we'll work our way up to what the picture looks like. But x squared, you may have already known it would graph to be a parabola, and this parabola is decreasing to increasing. So negative derivative to a positive derivative. So we're going to write our conclusions to the sign chart. Let's write them off on this side so we leave some extra space to come back and talk more about this. So where is the function increasing? We're actually going back and answering these questions. It says, where is it increasing? Where is it decreasing? So it's increasing after 5.5. So I would write 5.5 to infinity. That's where it has a positive derivative. And then decreasing is before 5.5. So you could say negative infinity, and just be super careful. You don't want to stop at 0 or 10 on any of these intervals. Those were random test values that I chose. We need to stop at the important number, the one that has an arrow to it. Negative infinity to 5.5 is where we switch. And then of course we know, because 5.5 is a critical number, here the derivative would have been 0, just like we pointed to on the graph. So our critical number has where the derivative is 0, and that's at our soft peak there. So we could take this a step further, which we're actually going to do in a little bit. We could find relative max and min. You might already know the answer of where it is, but we're going to look on the next page and try to visualize max and min.